Okay, it's 11:02, so I guess we can go ahead and start. First of all, thanks to all of you for coming to this webinar. My name is Shannon Hauk, and I'm a staff scientist at Q-Chem. It is my great pleasure to introduce our webinar speaker today, Dr. Xiaoliang Pan. Xiaoliang obtained his BSc in chemistry from Jilin University in 2006, and then his PhD in physical chemistry from that same university in 2012. And after that, he moved to the University of Arizona for his postdoc, and then he moved to the University of Oklahoma for a second postdoc, where he's been doing some really phenomenal work with Yuji Mao's group. And he has also been serving as a consultant for us at Q-Chem, and he's been working on extending Q-Chem and IQmol's QMMM functionalities. And also, just as a quick reminder before I hand this over, we will be having a Q&A session at the end. So if you have any questions throughout the presentation, please feel free to post them in the Q&A or the chat at the bottom, and we will get to those at the end. So without further ado, let's go ahead and turn it over. Xiaoliang, please go ahead.
Okay, first, I'd like to thank Shannon for the invitation for this seminar. And today I will talk about our work on how to use QMHub to do multi-scale free energy simulations, mainly for biochemical reactions, for example, enzyme catalysis. And if time permits, I will also do a demo of how to use IQmol to facilitate the preparation of these kind of simulations. Okay. So first, what exactly is multi-scale friend simulations? So in this context, we're talking about use a method called QMMM. So the idea is to divide the whole system into two parts. So one is the QM region that's usually involved in the reaction center of the system. For example, could be the substrate of the enzyme or some nearby side chain of the protein. So this example is the enzyme called Carsmate mutase. So here the QM region is the substrate, and the MM is the enzyme, and also the surrounding solvent environments. And by using QMM, we only need to use QM to describe, since this is the expensive part of the calculation. So we only use QM to describe a small portion of the whole system. So this will make this kind of calculation achievable. And also, we want to use free energy simulations instead of just simple energy pathway calculations. So these also require our cost to evaluate the energy to be as efficient as possible. And then we combine the QMM MD simulations with the free energy method. So for a very commonly used method is the umbrella sampling method. And the idea is to divide the whole reaction pathway into smaller windows. So this example, we are using the same reaction, this CO bond length and the CC bond length, and we define the difference of the two as our one-dimensional reaction coordinate. Then you see different colors are different windows or just parallel simulations to cover different areas of the reaction pathway. And to achieve this simulation, we just add a different bias potential on different windows to encourage the system to just sampling a certain region. And after we done this bias simulation, we'll do post-process analysis to recover the unbiased simulation results. So here we're interested in this free energy change along the reaction pathway. And the common use method includes the weighted histogram analysis method or multi-state banding acceptance ratio method, MBAR method. So this is the type of simulations we are interested in doing. But there's a few considerations that that motivate us to develop this QMHub software. So the first is what kind of boundary conditions do we choose? So since we are simulating a biosystem, so the better choice is we solvated the whole system into a periodic water box. Then this will reduce the boundary artifacts versus another commonly used model is the droplet model. And the droplet model, we will just use a water sphere with a certain radius. The typical choice is somewhere between 20 and 30 angstrom, centered around the QM region. Because the droplet model at the boundary, it is facing just the vacuum. So usually will be restrained to the starting position. So this will introduce some additional bias. Also, the long range interactions outside of this cutoff are either just not included or use some implicit solvent model to capture those. Another thing that we need to consider is what type of QM method to use. Since we are doing brand simulation that involves millions of single point force calculations during the MD. So if we use DFT, even the relatively cheaper ones are still might be too expensive for a lot of the system we are interested in. So one popular choice is empirical QM method, for example, AM1, PM3. But these type methods are usually not accurate enough. I'm showing example. The two methods gave us qualitatively different barrier height. So this can maybe lead you to like a inaccurate prediction. So, or even sometimes give you the wrong reaction mechanism. So that's something we need to pay attention to. Third thing we need to consider is the minimum energy versus minimum free energy. So minimum energy is just we optimize a single reaction pathway, and usually with the environment frozen in a certain configuration, and free energy pathway is we do the empty sampling. So we sample the average over. So the benefits of doing free energy is it will lower the bias of how you choose your starting point. So this is a figure from this paper. This just showing the variance of the barrier height between how you choose your initial structure. You see this is a wide distribution of the barrier. So this will give you very high uncertainty in your energy barrier prediction. So the key feature of the QMHub is to include accurate, also robust QMM electrostatics model that can capture the long-range QMM interactions while it doesn't introduce any discontinuities, because that's a lot of the common problem in this type of models. Also, what keep the cost as efficient as possible. So typical strategy to do QMM in an extended system is to divide the environment into two regions. So one is the near field region. So here, usually we will just use regular electrostatic embedding. That is the nuclei and the electron density just interact with the nearby point charges. And another choice of the embedding is this mechanical embedding. But here the QM charges are, QM atom just represented by a fixed set of charges. So you won't have any polarization effect from the environment. So usually this is not a good choice for biomolecular systems. And on the far field side, the long range part, this type of model will represent the QM atoms as a set of multipolar representations. So typically could be just point charges. And also you can also use point charge plus point dipoles to represent these QM atoms.
Okay.
So yeah, so first we want to test the accuracy of that. So we choose the QMM system that is a very large supercell. So it's not periodic, but just to mimic the periodic system. So we can have a reference calculation to compare with. And also we test several smoothing function between how we divide these nearby charges to make sure at the boundary, the energy function still continues. So the idea is for the nearby charges is be divided into two parts. So by this kind of switching function. So then whatever been switched off will be put into the long range part. So then the energy will be still continuous. And also we test several charge models to represent the QM atoms. So these several models just to, we benchmark the results here, it just to not include any long range part or use some fixed charge or molecular charge or ESP charge to represent them. And the story here is the molecular charge and also the truncation did poorly in respect of the electrostatic interactions, also the polarization. And if we use ESP charge, then we can get pretty good accuracy and even just 10 angstrom cutoff. So this is what we recommended to choose the cutoff. And this is also a typical choice for just pure MM simulations. So then we just use the same cutoff for both QM, MM, and MM cutoffs. Yeah, by doing the switch function, so some part of these nearby charges also be put into the long range part. So this is just make sure it continues at the boundary. Next, we implemented an analytical gradient for this model, so we can run MD simulations with this. And we first also validated by doing MVE MD simulations to check the energy conservation. And we can see the QMM model gave us the same energy drift compared to just regular MM simulations with the same PME. So these just to validate both the correctness of the gradient, also the continuity of the potential in the surface. Then with the model, we run some friend simulations and compare with the droplet model on the same enzyme system. And we can see it produce only slight different friend barrier. So that could be system dependent. So we're expecting for certain systems, it could have larger differences. And also the timing, even though we have captured the long range, including other periodic boxes, they actually are more efficient than droplet model. The reason is when we do this cutoff, this near field, far field division, after we do that, for the QM calculations, it only sees the charges in the near field. So for example, in this case, we use QChem to do this calculations. So we use the droplet and to include several thousands, like 8 to 9,000 point charges within the the single point DFT calculations. But with this argument charges model, for the DFT calculation, it will only need to include around 1,000 models. So this is where the saving comes from, even if we did some additional PME calculations. So yeah, that's the key feature of this QMHub. So the others are just usually just how to parse different input output from different packages. So here is the one type of calculation we do, the workflow. So this is how we run MD simulations, or this is like on the fly calculation of the usage of the QMHub. So in this case, we launch QMHub as a service running in the background. And then the MD engine, so in this example, we use a sender from the Ember tools. So in each MD step, the sender will send the coordinates and the charges of the system. So there were several mechanisms for this. So the most efficient will be this first in, first out pipe. And so this is, if we run on the fly, usually this is the best choice. And then after QMHub receive this information of the system at this step, we will do this QMM argument charges calculation to convert these could be tens of thousands of atoms. Then after the conversion, you only have the QM atoms plus surrounding nearby 1000 atoms. So these are sent into some QM engine we can use, for example, QChem or this SQM, there's a Samperco, but there are a few other options. Also, we can do machine learning type of models. For example, this can be just a PyTorch model. We load it in the same QMHub Python environment. And also we need another configuration file that just include, for example, what type of MD simulations, because several options. Also, what kind of switching function or cutoff distance we need. Also, the specification of all the QM packages also included here. So we don't need additional, for example, we don't need to manually prepare any QChem input. So this is the on-the-fly workflow. And another way to use QMHub is to use as a Python library. And this mainly used in the post-processing. And in this case, we just launch a Python environment, and then we can just import QMHub module. Then we have all the Python API of the module exposed to this Python environment. Then you can do any of these MM calculations within this environment. Yeah, next I will just show some research or methods that is enabled by this by the QMHub. So in the first example is we can use QMHub to parameterize a Samperco QMM model. So the motivation is just like I mentioned, the Samperco QMM method, even though they are very efficient, but the reliability is not usually very good. For example, in this just a simple S2 reaction in water, if we project the internal forces compare with the DFT one, then so each one is a force component. And if the dots on the diagonal, that means it's the same as the DFT force. So you can see the most important two force component is the force breaking for force forming distance is these two. And they're big systematic errors. And then we use the Samperco QMHub to reparameterize the model. So QMHub in this case will do post-processing to prepare the training data. Those are the force and energy, also the electrostatic potential and field on the MM atoms. And these are used as the training data. And also during the parameterization, we also can use QMHub to evaluate the empirical method at each of the optimization step. And these red dots are the after the optimization. So we see the much better agreement. Also, in terms of the reaction pathway, also the error distribution in energy are all improved just by doing the reparameterization. And this is the loss function we use. So as I mentioned, there are energy force, also electrostatic potential and the field from the on the MM sides. These are all optimized together. Yeah. Second example is we use QMHub to both train and inference machine learning potential. And I won't go to too much detail. And it's very similar to the empirical training. So we use this energy force and the potential in the field as the part of the loss function. And so we use QMHub to prepare this as a training data. And after the training is done, we'll use this on-the-fly mechanism to evaluate the same terms that's for future MD simulations. So this is also enabled by QMHub. So this is some results from this machine learning potential project. So here I'm showing these four quantities compared from the machine learning from the one model to this predict model versus the DFT results. So in this panel is the original empirical and the reparameterized. So the blue one are the reparameterized model. You see there's some improvement in the accuracy, but in this case, it's not, still has relatively large errors in the energy and the force. Then this next panel is the results from the machine learning potential. And we see the errors are even smaller compared with the reparameterized model. And these two colors just mean it's two rounds of training of the model. And the last one is a type of model called delta learning. So in these type models, the machine learning potential is not to predict the target model directly, but instead predict the difference. So here the results are the correction term from the machine learning on top of the PM3. That's the reparameterized model. So you can see even with one round training, it gives slightly better results than the two round of training of just doing this directly. And here's another way to benchmark the results. This just shows the energy error distribution. So we like to see peak distribution around the zero. That means the two models has high similarities. And with this machine model, we can also run same friendly simulations and compare with the DFT one. We can see this orange one is the PM3 star model. So it gives us decent results. But the two type of machine learning models give us even better prediction compared with the DFT one. Also, that's also can be seen from the sample pathway from these models. And lastly is the cost. So the machine learning potential is more expensive than empirical models, but it's still order of magnitude cheaper than the DFT one. Also, things you need to keep in mind in terms of cost is both empirical and DFT1 has either cubic or higher scaling. So this is just a 22 atom system. And the machine model is formally a linear scaling. So you can expecting when we scale up the QM size, the machine model can be either on par of the empirical or could be even cheaper once you have larger size. So another type of calculation that we do is this reference potential method. So the idea is we pick two tier of methods. So one is the low level one, to one the higher one. Then during the sampling phase, we only evaluate the low level methods. And then we do this this is umbrella sampling. And for each window, we will do this vertical correction, just doing single point energy calculations for the collected configurations in each window. So for this one, we can use QMHub to do this single point calculations at two levels. Then this can recover the high energy function without really using the high energy function to run sampling. And also this type of correction is can benefit from the good overlap of the two level theories. So this I'm showing, we do the same correction, but with the standard empirical PM3 or the reparameterized one. And you can see if we improve the similarity of the two methods, this can give us a much better prediction from this kind of friend perturbation type of correction. And also, this is a similar story. We also have a good sampling of the pathway. And since this is a reparameterization, so it doesn't add any additional calculation during the simulation time. So we just pay a small cost to do the reparameterization. Okay, next method is the previous one are all post-processing method, but this one is a on-the-fly method. So in this case, we are adopting this RESPA multiple time step scheme. So the idea is to, if we can separate the force of the system into some fast components and some slow components, then we can use different time steps for to rerun simulation components. And if we can construct our system in a way, the slow components that's also slower to evaluate. So you can see this can enable us to run faster simulations. So in context of the QMM, multiple time scale simulations, we construct the fast components to be the low level method. So that could be just a empirical method. And then the slow components will be the difference of the high level methods and the lower level methods. So you can see after you add them together, you recover the high level method. But this enables us to only evaluate this high level at this other time step. So this could be beyond the typical 1 femtosecond MD time steps. So we also test this on this Corsame mutate system. And we first try to validate, is this separation is a valid assumption? We can have these fast and slow components. So here I'm showing the blue one are the force components from the original DFT. You can see there's several high peaks in the high frequency region from especially these hydrogen atoms. So that's kind of expected. After we do this separation, now we only evaluate the difference now. So the difference is these two colors using the two sample methods. See, those high frequency components are greatly reduced. So this enables us to evaluate these slow components using the larger time step. Then we tested the different step size from 2 femtoseconds up to 8 femtoseconds, while keep the inner step 1 femtosecond. So these plot shows us, even though we stretch the outer stem cell to as far as a femtosecond, it can still produce almost the same Fourier profile. And by doing this separation, this gives us pretty good acceleration without doing any reparameterization. Okay, I think this is the last project on the highlight is the also post-processing analysis that's enabled by QMHub. So in this case, it is used in analysis tool. So that's the idea is to how can we extract more physical insights from just the friend simulation besides the friend barrier or barrier height. Yeah, like I mentioned earlier, the typical analysis tool we use for oversampling is WAM or M-bar methods. But these methods is based on estimating the probability of the reaction coordinate along the pathway. So it doesn't directly use the force information. But another term for the friendly profile is even though there's some subtle differences, the potential of mean force idea. So we are this method is based on this using the mean force that's from the physical energy. We do this thermodynamic derivation on the. So the benefit of doing that is now we have the explicit energy term in this mean force expression. Then the total energy, then we can just do energy decomposition into different terms. For example, for the QMM interaction energy and also this MM energy itself. Then this QM part can be further decomposed into just isolated QM atom, plus the permanent electrostatics. That's the isolated QM interact with MM directly without any relaxation of the electron density. Then we will relax the electron density, and the difference between the two will be this polarization energy, plus the van der Waals interaction. That's typically just handled at a force field level. So with this decomposition, these last three terms are interactions and energies between QM and MM parts. Then we can further decompose into the contribution of each of these into contribution from each of the MM atoms. So then this will be just sum over this. B will be the index for the MM atoms. So you can see this can be very nicely decomposed to different components. And the benefit of doing that is first we validate if this analysis can produce the same results as the standard one for the M-bar. First, we compare the two. That's gave us confidence. So we're doing the right thing here. Then the benefit is now we can do this TI or thermodynamic integration using only the components of the atom terms. So then this we can just show the Fourier profile of each of the components. So for example, here we can see if we integrating the gas phase or isolated QM forces, we'll get about 20 kcal per mole barrier. And then the actual barrier is around 12, I think. Yeah. And the difference is mainly comes from this permanent electrostatic interaction between the QM and MM. So we can say the MM environment or the enzyme bring down this barrier by the mostly the permanent electrolytes, and the polarization effects is relatively small. I think it's only 10% of the total contribution. And the van der Waals interaction in this case is almost negligible. So this can give us a very nice physical picture of this mechanism. And also because we can do the decomposition by atom, so we can group the contribution from different atoms just by residue. Then we can see the contribution of each of the residue in the protein. So you can see the majority of the barrier, lowering of the barriers come from just this single residue. That's this arginine 90 from the chain B of this is a trimer. So this is the one chain of this residue. And also there's several others provide relatively smaller contributions, and also a small portion actually is like bring up the barrier for some reason. Yeah, this gave us very rich information from just this calculation. And here I'm just highlighting the important residues, or the residue that contribute largely to the change of the barrier into a table. Then we can use these to guide our mutation if we want to like improve the efficiency of the enzyme. And also we can use these to do some nice visualization. So here the color represents the contribution for the residue, or actually the atom, divided by its charge. So then we can see a good separation of the region. And in the red region, we see has a negative potential. That means you can put positively charged residue in this region. So we can have a negative effects on the barrier. And vice versa, we can put negative charge residues in this blue region to do similar things. Okay, I think I should have some time to do a demo. And first I want to show just the example of the input for the QMHub. So on the left is just the snippets of the Amber inputs. That's something just show how to modify the Amber inputs to run a QMHub. And mostly is unchanged in this QMM section. Besides, we want to use a very large QM card in this case. So the reason is the QM MM interaction, the division is handled inside the QMHub. So we want Amber to give the full system to QMHub. So also we want to turn off the QMMU or the PME with the Amber too, because these are also handled inside QMHub. And on the right side is the example of the QMHub configuration file. So I'm showing this example is to run a PyTorch model. So in the first section, we specify the switching function cutoff, and also we want to run periodic boundary conditions or not conditions here. Then what type of engine to use? So in this example, we will use the PyTorch to run a machine learning potential model, but this could be Q-Chem or SQM. Then in the later section, you can have actually more than one engine here. If, for example, the multiple time step, and you want to specify engine 1 and engine 2. For each engine, you need to put the keywords for each. For example, this is a path model for PyTorch, and for Q-Chem, that could be the method or basis set we use. And later, I will do a quick demo of how to use IQmol. So this is a unreleased feature that's in development. So we can use IQmol to prepare QMM systems, or including QMM input files for certain MD packages. So I will demoing how to use QMHub to prepare an Amber system to run QMM. Okay, before I do the demo, want thank a few people. And so first is for the QMHub project, and would like to thank my advisor Ihan, and also a collaborator Adina for the early conceptualization of this project. Also for the third part, I also like to thank Dr. Xiao and also Kuan Honan for the theory, and also Andy for providing the PME code, and Richard for testing the code, also using it in his research, and Daniel for the documentation, and also Rafik for helping me pour the QMHub to the Charm platform. And for the IQmol project, definitely I would thank Andrew for his help in the development. Also, I owe all my GUI development skills to Andrew, so I learned a lot from him. And also the conceptualization of use QMHub to facilitate the preparation for the QMM calculations is from Yihan, also Yuji, and Chance for testing the code, also carrying on the future development. Last and not least is the whole Shell group for all the support during the years. Also, the QChem team for giving me the opportunity to work on this IQmol project. Yeah, also other help during this time. Okay, thanks to the demo. Yeah, I think to do this relatively quick, so we have some time for questions. So first, I will make a directory for this, and let me launch IQmol first. Okay, so usually the simulation start from a PDB file. So I will demoing with this particular one, that is an enzyme with a cofactor called SAN, and okay, it has between to turn this inhibitor into this substrate. That's all will be done here. So let me download the PDB. Okay. So yeah, I will first load it. Okay, the PDB is here, so we can first visualize in IQmol. Okay, here we can see the protein, the cofactor, and the substrate. And like I said, this is not its natural substrate. So we need to do some modifications. So first I will highlight the two side chains, and then I'll click here to delete them. Okay, now it is the substrate. And I will just also rename here to make sure. Yeah. Okay. Before when we run the MD simulation, we need to provide anything that's not the residue that's been pre-parameterized in Amber. So in order to do the partial charge, we need to assign the correct coordination state. So we do that by doing these hydrogens. Okay, now you see it's pronated. Since we know the reaction will be the methyl group transfer from the SAM to this substrate. So this oxygen will be the acceptor of the methyl group. And in order to happen, you need to be on difference. And since we want to only focus on the methyl transfers, we will just pre-deprotonate it by just highlight this and delete that one in the system. Okay, so now this one is protonated. Now we will do the same thing for the SEM sun hydrogens. Okay. So we also need to manually change, deprotonate this carboxyl group because most likely they'll be deprotonated in this neutral pH environment. Okay, now these are properly chemically modified and protonated. I will launch this Amber system builder. Okay. Oh. Okay, in this window, on the left side is options, right side is the TLEAP input file for this Amber, for the TLEAP program in the Amber tools. So in the first section is the force field we like to choose. So on this part, the left box contains all the options provided by Amber tools, and the right side is the ones we pick for the system. So we can just pick and choose what you want. So I think tip 3P looks good. Yeah. So you see, whenever I modify here, the right side will be updated in real time. So now we have decided the protein and the water model, also the GAF2 for the ligand. Now we need to parameterize the two small molecules separately. So here, okay, so for this one, the charge and the multiplicity looks good. Also, the force field is the one we want. Just click run. And in the background, IQmol will launch the anti-chamber program and to calculate the partial charge for this first one. And while it's running, we can also launch the second one. And here, notice the charge is not correct because this one deprotonated, so it need to be -2. So then this multiplicity also be updated accordingly. Then we can run the same permutation. Since this one is smaller, see, it takes shorter finish. So after click, we see here these two fields are also automatically filled in. Also, this one also finished. So this is the two files contains the information from the anti-chamber partial charge calculation. Okay, that's done. And also the right side also updated. Next is the solvent box. So we just choose the rectangular box with the tip 3P and the buffer distance. So this looks good. Then the counter ions. And in this case, I will just use sodium plus 0. 0 means the TLEAP will put just the right amount of charges to neutralize system. So this can be a good default choice. And on the right side, you see it's all reflecting whatever we have chosen in the left side. And since these options haven't covered all the options, so you might want to do some menu modifications. If that's the case, you can just click here, then do your menu modifications within. Then once you're happy, you can just click to run. That will launch the TLEAP calculation. I will do the assignment of the parameters, also adding solvents and the counter ions. Yeah, so this might take 1 minute. Yeah, so after that, we will see, yeah, see is some intermediate files. So for example, the parameter files for the two ligands. And in the end, we want to have, okay, finish two. Yeah, so in the end, we want these two files for the MD simulations. So that's these two files here. Yeah, okay. Yeah, that's the demo. Okay, now I'm ready for questions.
So thank you so much. That was a great presentation. And thank you for the good talk and for the demo. I do have one quick clarification. At the beginning, I definitely said that you've been doing a lot of work collaborating with Yushi's group, which I think accidentally implied that you were a postdoc in his group. So just to clarify, yeah, Xiaoliang is a postdoc in Yihan
Yep.
Xiao's group. So sorry about that. But yeah, so Kuan Yu has asked where can he download this version of IQmol? And does he need to download QMHub? And how
Right
does
now, these
IQmol
two are separate. Yeah, so right now, there's no overlap between the two. So on the new version of the IQmol is still this official repo, but in a branch called GrowMax. But that's also include the Ember parts. The reason it's called GrowMax is that's the works, the MD engine that's first been developed for. So I think that's a reason for the name, but it is also include the Ember parts in the GrowMax.
Okay. So
Yeah.
yeah, and then I think
Yeah.
this version of IQmol isn't quite released yet. Is that
There's no binary release, but the branch is open, so anyone can download and compile.
Mhm. So, but
Yeah.
it is a separate branch of
Yes.
IQmol
Yes.
on
Separate
GitHub,
branch.
I believe.
Yes.
And I can put the response to that in the chat, I suppose. And then the follow-up question to that is sort of how does IQmol find Amber, QChem, and QMHub? So like on sort of the back end, I suppose.
Oh yeah. You mean how the find Amber, right?
Yeah, like
So it's in
how
this
to
config.
link IQmol to it, I suppose. Yeah.
Oh, it's just doing system call to the Amber executable. So you just need to provide the installation paths of the Ember tools. So in this case, because Ember tools has a Conda version, I think that's probably the easiest way to install it. So you just need to have a Conda environment. Then you just Conda install. I think it's in the Conda Forge channel and this Ember tools. Yeah. And it supports most of the platforms. So I would say this is the easiest way to get Ember tools. Then once you install that, you see here, I'm just providing from this environment, Conda environment as the Ember home. Yeah. Also, before you can doing that, there's also an option here, this Ember support that's need to in this global IQmol preference. So after you enable this, you will see these three options. But yeah.
Okay. So I guess my follow-up question is where do I find this branch of IQmol? Because I'm looking for it in the main IQmol repository and can't
Oh,
find it.
yeah.
Have you forked your own copy of it? Is that
Let me double check. It should be here. Here, this one, Max.
Oh, it's
You
under
see?
IQmol 3. Okay, I see.
Oh yeah, that's
Okay, understood.
that's probably something Andrew need to do
Update
something about. Yeah, that's very confusing. Remember, the IQmol is relatively 2 years old. So
that. Okay,
any development is in the IQmol 3 repo. Yeah. So here you see there are many new updates to this branch.
okay. So I've just answered as a response
Yeah,
to this
this
question.
3 is
And I'll
important.
also post it in the chat, and then for anyone watching this on YouTube later, I will also put it in the YouTube comments, in the little description underneath the thing. So, because I think there are quite a few people who are interested in this particular development. So, and then yeah, Kwani says thanks. So are there any other questions? Because I think we're just about hitting 12. And I don't want to keep you too much longer. But does anyone else have any questions? Okay, awesome. Well, if no one else has anything, then if you think of something later, you're always welcome to reach out. I'm going to be posting a topic on the forum with sort of a Q&A section if anyone has questions that they want to ask after the webinar, if something occurs to you, a couple days from now and you go, oh, I wish I'd asked that. Then we'll be happy to answer that there. Thank you again for an awesome webinar. And it was very enjoyable.
Yeah, thank you.
QMHub is a little outside my usual, I guess, domain of things, and so I'm learning a lot. And yeah, like I said, I know a lot of people, particularly about the IQmol Amber setup, are quite excited about these developments. So yeah, thank you. All right. Thank you, everyone. And thanks again to Xiaoliang for a great webinar. And yeah, thanks, everyone. Bye.
Yeah, bye.